Hello everybody, hope you're having a good Monday, and got another supermoon going on here. Seems like we're having those every month, but the moon is a little bit closer than usual to the Earth as usual, 7% closer than usual. It's not a whole lot, so I was trying to find out what time it is. I've got 23:30 UTC, so that was either an hour ago, which I think it is, or it could be 23 hours from now. Sorry, I'm not sure which one it is. But let's see here. Actually, no, that's the time of the supermoon. That's when the closest approach is, and then the full moon comes tomorrow at 00 23 hours. And the Geminids meteor shower tomorrow night, so you probably want to keep an eye on that. This is the temperature anomaly for North America. Things looking pretty cold up in the north part of the country, and very warm down in the south part of the country. When we have that kind of setup, that is a good pattern for zonal flow east to west. So those upper level patterns, those are driven by the surface temperature contrasts. So when we have pretty much everything up here being cold, everything down here being warm, that's what will set up a very strong zonal component. And let's see, it looks like the coldest weather, the coolest unseasonably cold weather looks like it's in the Dakotas. And for the warmest, we're looking at Louisiana and New Mexico. Texas is kind of in between, and that's because we've got that old polar air mass still in place over Texas, and the return flow has tried to erode that, but hasn't made much progress. There's some of that cooler air kind of hanging on there. Surface chart looking like this. And let me switch over to chat and make sure everything is up and running. Let's see here. Okay, Michael says he's in Georgia. Okay, appreciate that. All right, I think we're good to go here. So let's take a look at Texas on the south part of that frontal boundary. Looks like the surface front is still well to the south, but just far north enough in Louisiana to bring the temperatures up a little bit here. And you can see there's pretty much the core of the cooler air. And it looks like we have another reinforcing shot coming from the northwest. And where's the leading edge of that? Looks like that is in southern Nebraska, located about right there. So we'll look for that on the thickness and isobar chart. And let's move that over real quick. And we can see, yeah, very strong temperature gradient east to west. And now remember, thickness is going to be kind of like your average temperature in the lower troposphere. 1,000 through 500 millibar thickness. That's surface through 18,000. So this is the strongest band of temperature gradients, and looks like another gradient right up here, and that's associated with the leading edge of that new polar reinforcement coming through Nebraska, Iowa, and Minnesota. And then that old frontal boundary is well to the south, and probably a piece of it extends into Arizona and into California. You can see that gradient running right through there. See if we can detect that. Fronts are very hard to pick out in the western states on surface charts. And yeah, this is pretty hard to detect. We do see kind of a very weak northerly flow there in Nevada. 30s and 40s, that's kind of about average for this time of year. And things look kind of warm down here, kind of a weak southerly flow. So yeah, this gradient is pretty hard to find, so we're probably looking at maybe something in here. So we'll go back to that one chart and just finish this off. So that's kind of like the basic setup, and we can look out in the Pacific and things look pretty quiet out there. The next system in line is way off to the west. So probably we will see that coming down the line over the next couple of days, things being quiet in this part of the country here. around the 14th, 15th. Core of the polar air mass right there. Not over the Canadian high Arctic, but over northern Manitoba. Let me see if I can take a look at the soundings up there. Take a look at the UCAR sounding. And they don't go quite very far north, so we probably have to do the University of Wyoming. They've got pretty much worldwide coverage there. So we'll click on YYQ. That's going to be Churchill, one of the polar bear capitals of the world. And there's our sounding. You can see it's way over on the left, showing you just how cold this column is. And it looks like a little bit of Arctic air right here in the lowest 1,000 or 2,000 feet of the atmosphere. The rest of it is very cold polar air. The tropopause, that's up at about 20,000 feet, and above that, stratosphere. Oh yeah, and you can see around that polar vortex in Churchill, they're pretty much in the deepest part of the cold air, and you can see there's kind of a weak wind profile. There's not very much temperature advection, so that area is fairly barotropic. The satellite picture looking like this. We haven't done satellite pictures in a while. This is infrared. You have to kind of know which type of imagery you're looking at, whether it's infrared, water vapor, multispectral, or visible. So we're actually looking at temperature, and the coldest temperatures are highlighted because this is an enhanced IR. So this is going to be especially cold right here. That's going to be cirrus tops there in Missouri. And what we have up here in northern Canada, that may not be cirrus. That may actually just be the cold polar air. Let's see just how cold that is. Let's take a look up there in northern Manitoba. This is in Fahrenheit. We've got some -30 readings way up here. So that's pretty darn cold. And sub-zero readings pretty much all the way down to the Dakotas. And then you go up to the Canadian high Arctic, and it actually warms up just a little bit. Only -10 up in this area, and then a few -30s up in this area. So yeah, that is the core of the polar air, and consequently, because the ground is so cold, it's very hard to detect cirrus because they tend to be about the same temperature. So this is where you kind of have to wait till the daytime and look at visible imagery, and then kind of track that using continuity. And elsewhere, looks like a squall line just off the east coast there. Pretty cool there. It'd be pretty neat if you're out there on one of those merchant vessels. Okay, so we'll go ahead and head right into the forecast. I think that's about all there is to look at. Pretty quiet evening here. So there's that first front coming down, and the old polar front, kind of like that. So, for our webcast tomorrow, going to be Tuesday here. Looks like that front moves southward, and that's going to give us kind of a reinforcing shot here in Texas. Winds should turn from the north during the day tomorrow. And here's that old frontal boundary. Looks like it lifts northward into Nevada and Utah. And looks like another system kind of creeping there into the western part of the image. But overall, fairly quiet here. Then for Wednesday, looks like more cold polar air shifting southward. I guess it would be sifting out of the polar regions there. But yeah, there's the polar core right there over Ontario. So that's kind of moved southeastward. I guess you guys can't see that. There we go. There's the core of that polar air. So that's kind of moved down this way. Very cold pattern there in Ontario and Quebec. Then for Thursday, let's see what we got here. More of the same. Big polar high right there. That's probably just a chunk of that polar air being driven southeastward. And then on the western fringes, we're starting to get a little bit of cyclogenesis out here, especially in California right here. So you can see a lot of rain and precip there during the day Thursday. Then Friday, that comes across the Rockies, and we start developing some good isentropic lift along this next outbreak coming out of Canada, and very strong cyclogenesis in the plains. That's going to spell kind of a warm advection pattern across Texas and Arkansas there on Friday. Then Saturday, we get a little bit of a cold surge coming into Texas. So leading edge looking like this. That's going to be kind of like a blue norther coming on down through Dallas and Oklahoma City and Abilene. And getting a little bit of precip on the backside of the front. So you can see this is kind of a Anna front. So this almost definitely shows we got a little bit of an upslope component up the isentropic surfaces, kind of that in that direction. Either that or this cold air is just plowing right underneath it and lifting those layers. Then for Sunday, that kind of just sweeps southeastward through the rest of the southeast, and there's our high pressure areas. And then we get this big cyclone developing up in Canada, so things should moderate a little bit up here. Kind of a stagnant pattern there for the 20th and 21st, and probably all the way to Christmas Eve. Looks like down in Texas around the 21st we start developing a little bit of shower activity. That's probably a little bit of isentropic lift with the remains of that cold polar air mass. As we've seen, that takes quite a long time to dislodge when they're coming out of Canada that deep. Then the models around the 22nd, they go for a big blast of cool air from, this is going to be more Pacific in origin. The only thing is it's showing a rather cold thickness pattern here, 528s all the way to the Red River on the 23rd. So that's kind of more, when I see that, I'm thinking maybe more of an origin of Western Canada. So I'm not quite sure if that's going to, if we're actually going to see that. This is 260 hours out. But in any case, it looks pretty cold across maybe this part of the country on Christmas. Then another blast of cold air coming on down and developing some wintry precip on the 27th. And I think we're about to the end of the run there, but it looks like GFS suggesting a new system coming together. Okay, let me see if there's any comments about that. I'll just check on the chat real quick. Sarah got 7.5 inches, and if my memory's correct, she's in Indiana. And yeah, I got Lloyd here in New York. Probably pretty cold up there. We got up to like 65 here. Temperatures came back up. They started out pretty cold here this morning, but we got those ladybugs starting to come out yet again. All right, so I guess that brings us to our next segment here. Okay, yeah, that's going to be, we're going to talk about just a little bit about frontogenesis. So what's the definition of frontogenesis? You probably think of it maybe as the creation of a cold front or a frontal zone. And yeah, that's correct, but it's actually good not to look at the atmosphere in terms of objects like that, but actually gradients. So we're actually talking about the intensification of a temperature gradient. And if we want to get more technical, that's actually the intensification of a potential temperature gradient. But for a constant level like the surface or 850, that's going to be about the same. Basically, the intensification of a temperature gradient. Now, one way you can get this is to just have patterns that bring contrast very close together. So you can see there's a temperature gradient right here. So frontogenesis is actually going to be intensifying that by having convergence working on that. So that's actually what we have going on here. Didn't do a good job drawing that. So here, yeah, you can see some convergence. And the gradient looks like that. So that's bringing that together, and that's given us frontogenesis. Now, another way we can get that is through, especially when you're in a weak pattern, you're not going to have low pressure areas. You're going to have what we call deformation zones. And that's where the wind comes together and kind of fans out and kind of forms a box. And that might be a little hard to kind of follow, but I might be able to show that using current data. So let me do a plot here of the winds. Let me just actually use the surface data. Okay, I do think we have a low pressure area right there, but further north I think we do have kind of a weak deformation zone. So we're talking maybe Nebraska. You see the winds coming out of the north here, and they're coming out of the south here. We don't have well-developed low pressure in this area. But if we do the streamline analysis, we're going to come up probably with, let's see, a little bit of convergence in this area. I can almost see kind of like a weak deformation zone, kind of like that. So there we go. So you kind of see we're kind of developing that pattern that we saw on that last slide there. So the actual zone is looking like that. Now, where this becomes important in these weak regimes is the orientation of the temperature gradient. And I can just plot that real quick here. So this is the temperature gradient. That doesn't look right. I think something's off here, because I see 19 degrees here. The plots are showing 26. But anyway, let me just replot this, and I'll just kind of draw it where the gradient is. So gradient kind of like that. The deformation zone is kind of like that. And what's actually important is the relationship of that gradient to the deformation zone. So when you have it oriented like this, obviously you're bringing temperature contrast close together, and that's giving you frontogenesis. Now, if we had the isotherms kind of like this, and our deformation zone was like that, this would actually be frontolysis. This would be the breaking up of a frontal gradient, because these difluent lines here are pulling the gradient apart. So to summarize here, I'll show you this one graphic. This may make it a little bit easier. This is from one of Bluestein's books, and this shows the deformation zone here. And what's important here is to look at the orientation of that temperature gradient to the deformation zone. So here you can see that the convergence is bringing them together, so this is frontogenesis. So that's increasing the temperature gradient and strengthening your frontal zone. And this is frontolysis. So here what's dominant is the difluence pulling the gradient apart. So over time you're going to have these dash lines, these temperature lines, they're going to spread out. So that's one little simple concept you can look at, and there's other things that act on frontogenesis and frontolysis. It's not just that, but there's things like tilting and diabatic processes. But that's just one thing you can look at right there. And yeah, here's let's see here. Yeah, this is probably showing you a little bit about that deformation zone here. Actually, I'm trying to figure out how exactly that. Yeah, I think what we're seeing here on the 850, this is up at 850 millibars. So with that, we're going to get, this is showing more of a convergent pattern. So any convergence where you have a gradient right here, that's probably we're gonna see that's gonna, let me draw that out just a little bit here. So you can see here the gradient coming together in this area. So that's going to increase the temperature gradient right there. So this is actually an area of frontogenesis right there. So anyway, yeah, feel free to look at these. The way to get that chart, SPC mesoscale analysis, and go to that menu up here. 850 millibar will give you a good indication of what's going on in the lower boundary layer. And you can use that to kind of look at the thermal field in the central and eastern U.S. and see what that's doing. So if we were going to do that in the East Coast, everything is pretty much offshore, but this does show you your cold pool and your wind flow on top of that. So here we're seeing an area of cold air advection, and here an area of warm air advection. So anyway, I didn't want to make that too long. I'm still kind of trying to work out this building block thing, and I hope to keep it under a minute, so sorry about that. Okay, I think that's about all I got for tonight. Let me just check over on chat and see if anybody has any questions. And, yeah, ladybugs, those things. Hopefully we'll be rid of those things soon. Anyway, I appreciate you watching, and hopefully we'll see you tomorrow at 8 o'clock. If you have noticed any big freezing of the video and need to report that, just let me know or type that in text. Anyway, thanks, and we'll see you tomorrow.
Mm-hmm.